Hello everyone. In this video I will try to show you how to diagnose CD3217 problem. If it's already swiped, so you had like a pretty clear case, or better to say my partner had a pretty clear case. There was burned CD3217, so the secondary chip. He replaced one chip, it didn't work. He replaced both chip from known good working board. So it was actually tested, it was giving 20 volts. So we have board basically works, but it's stuck at 5 volt. So won't charge the battery, obviously. So we are gonna try to figure out what's happened with it. And I will try also to explain nearby how CD3217 works. So let's get our board view. Okay, we got it here. We have our power meter. Where is it? Okay, so the first, let's see what it does. So let's draw some graph here. Okay, so let's create new and let's record it. Okay, so nothing really interesting here. So we have 5 volts all the time. We have probably boot of the T2, not the T2, I'm sorry, no, the M1 to the state of probably iBoot stage 2, so it should now turn on SSD. There should be almost all powers present, and it should communicate with charger, but it doesn't. So it basically it loops from this moment and so on. So it just goes to 0 amps, then it resets the charger, and now it's likely, yeah, so 5 volt reset. PP bus generated 3.8 NAND power supply, full power off, reset. So we know that board properly works because we charge the battery with other main board, and we know 100% the device is fully operational. It doesn't recognize any USB devices, so nothing working on the USB line. So now let's check what's going on here. So always look optically, or if you find something. So the board was soldered, already partially cleaned. So there are 2 ASD diodes missing. It was also listed. There was a attempted repair on this machine, so it's not bad. Both CD3217s are soldered fine. They are both come from working board. I can't see anything suspicious here. There was no water damage, just all of a sudden one of CD217s died. Okay. Okay, now, so since we know that battery it works on batteries, there's basically no reason to check any further lines like your PP bus, or to check 3.8 or any other power supplies. Basically it's all completely fine, so 100% fine. So we're gonna start with checking if we have some activity, if CD3217 tries to boot its firmware, because this is probably what's missing now. So the chip is like brain dead. It only allows 5 volt through, and board kind of turns on for this 5 volts. It generates 12.3 volt PP bus, and it's recognizes there's no charging IC present, and it just boot loops, tries over and over again. Okay, so now let's go to the for export to. And now we are going to find we can use clock, or we can use master in slave out. So master in slave out means that master, which is in this case CD3217, is listening to the to data. So it's receiving firmware, and it should happen here on this this resistor. So let's put it here, and let's I'm not sure it will be visible, and so it's easier, but the screen is not that nice. No, that's a shame. So this one is pretty basic thing from FNIRC, and it looks like in camera I don't see anything on screen. Maybe there's some settings here. Menu, Einstellung. Okay, it's already on 100% brightness. So yeah, this thing is quite handy. It has oscilloscope, it has signal generator and so on. Well, let's hope it will be. Well, at least it's something is visible, so the pattern of reading some stuff is pretty clear. Since we have boot looping, we should have seen any activity here, so there's nothing happening here. So the same thing we need to check if there is chip select active. So there's also nothing, absolutely nothing. Let's check. So at this point it's already useless to try to flash the firmware and to add, like more stuff. You need probably to check again if you find the solution. Okay, so master out, slave in. That would be our next point of interest, because to write something or to read something, you need first to get to send command for it, and we see absolutely nothing here as well. It's also 0 volt. All right, so now it seems that we have some problem with our firmware reading, so it's not able to read the firmware. So the next thing we're gonna check, and by the way, the broken CD3217 was the lower one, so the slave, so master seemed to be fine. It was also replaced, but still, I wonder what would have happened to cause this type of problem. And such devices, they should be fixed in 100% cases, because you know that the device is working, you know that the device only needs charging circuit to operate, and it's not a rocket science to fix a charging circuit, so like 100% of charging circuits should be repairable per definition. There's no such case as non-fixable charging circuit. Okay, now let's check some diode readings. Let's check if any line is in short or open line. Let's start with MOC, master out, slave in. Both are fine. So MOC here, let's go with miss with Okay, so MISO was fine. Let's find the MOSI. Where is it? Here we go. The first one. It's also fine. So let's check what's going on from the... Obviously also everything's fine. Okay. So the readings of MISO is okay. Let's check chip select. SPI UPC. Okay, so let's move this chip select resistance, because I believe this one is pass-through resistance and there should not be any difference in readings of the in diode mode. So maybe this trace is broken. I'm not sure, but still worth checking. Also might be useless step to do. But let's check it. And by the way, reading firmware is absolutely independent from anything. So the chip, if it got power, if it got on rails, it should read the firmware. It doesn't need some reset signal or whatever. Wrong orientation. Okay. Okay, this trace is working. So what I did, I removed this this resistor just to see in the diode board if we have any reading. That would mean that we have trace to the chip, because chip itself will have signal processor for this line, which will act as a diode, or maybe it has like ESD protection internally. I'm not 100% sure why exactly, but almost every data line has some sort of diode readings, which is a common way to figure if you have connectivity. Okay, so, oh, hello, I want to put you back. So it stays on tweezers. No. Just need some flux, because it shows flux and it's already degraded. Okay, let's take a closer look here. Alright, everything seems fine from this side. And by the way, I forgot to check diode mode for ports, because maybe we have some sign of problem if we read diode here. obviously it's I'm not quite sure. Maybe there's something, or maybe the cable is bad, because I think I seen bad cable somewhere here on the table. Okay, this one is weird. Really weird readings here. Let's put a different one. And here we will put a question mark. Most likely. No, it's not the cable. So we have I think we found at least some clue of the problem. So you can see it. I'm sorry about that. Okay, so we have bad reading on one of the USB lines in the middle. I can't remember which one, but it's definitely not okay. This is a bad reading. This is okay, and this is not okay. We have 0.07 ohms to ground on one of the USB lines. So maybe this is just trivial repair. Interesting. Let's find this USB which is bad. So I believe we are going to go on the top side. Somewhere in middle. So this one, 0.7, 0.7, this line. Okay, this is the other side. Okay. Yep. Okay. I'll put this. It's actually a good idea to mark it so I won't forget. Here we have a white. Here we have a red. Oh, yeah. Here we have a red pointer. So I just marked which side goes where. Actually, I had like stickers for this thing, but you know, last time the smaller kid, he just wanted to play with this stuff, and since then I don't have stickers anymore, and I somehow lost or deleted the file I made it from, and I don't have enough time to restore it yet. Okay, so we have one of the USB lines shorted to ground. Let's look what's going on here and how could it be. So let's go and check. No, this one. So it was the upper. Okay, let's rotate the board. Let's turn on the board view. Let's locate this thing. All right. it should be channel 0, I guess. USB-C bottom 1, probably. Oh, you go exactly. Okay, now let's simply remove CD32. Or maybe move this ESD diodes aside, just to check it. Bottom N, SPU. Okay, so it should be one of these. These are the bugs. Okay, this is SPU. Okay, so it's one of these 4. 1, 2, 3, 4. We only need to move 2 of the. No, we'll first test a test point. We have a test point here. I am dumb. Maybe we don't need to solder. This one is fine. This one is fine. Okay, it's one of these 2. We are removing both ESD diodes, simply to check if one of them is a problem. If not, we have no options left but to replace CD3217 once again. Maybe it was a problem all along. Then this video won't be really interesting. I will probably still post it as a raw video. And I'll put useless diagnostics. Because, you know, sometimes you can actually mix 2 chips and put a bad one once again on board. It happens. Zero 05, 06. Okay. Let's put it once again. Did I miscalculated the position? No, I don't think so. I don't think so. Oh, it's fine now. Look at that. So let's try it right now. Come on. No, we don't have 20 volts. We have the same reset, but we have one problem less. So it's not easy fix now. Anyway, let's still check if we have activity on Thunderbolt. I don't think that would fix it. Yeah, and it didn't. So this CD3217 is still not working. Let's go to the schematics and look a bit further. You all know this feeling when you already did everything, you already wasted lots of time for easy fix board. You just, oh, I will just swap it, it will work. Or maybe if it won't work, I will simply go and like take another board and put non-good chips on it. It should work. Oh no, it's not working. What are we gonna do now? So now let's look a little bit deeper and what do we need for this chip to operate. So obviously we have power input here. So we have main input, PP highway, so V bus is our output. We need to check the first thing I usually check is LDO line. So let's check for the 3.3 LDO, so this is internal power supply. It's also used for SPI ROM reading. It was there because we seen 3.3 level on this line, so it's fine. Okay, S2 UPC. This is 3.3 volts provided from the system, so that's why it's pulsing. This is fine. Let's go to the there's also 1.5 LDO core, so probably power for internal core supply. It's also fine. Okay, so we have all LDOs. Okay, the next thing we're gonna check, there's VDD IO. This is 1.2225 S2. Unfortunately, it will be there because otherwise it would not work. I mean, the board wouldn't work from the working battery. At least I think so, not 100% sure. But okay, so these two caps seem to have the same line here. We have 1.2225. This is also fine. Okay, so we have voltage inputs, we have everything. The next thing, let's check the UPC SS. This is that's some more power supplies. And there's nothing. I think there should be something on this thing. I think it shouldn't be on 0. Okay. Or maybe it's not used in this point. SS UPC 0 SS. Let's check the ground. It's all right. But no voltage on both chips. It's not on first. It's not on second. Okay. Let's check USB lines here on the coil. Okay, in diode mode. It's fine. It's fine. This is fine. And the sad thing about such repairs, you can't really say I'm out of ideas, because this repair is always trivial. There's always something simple missing. And you can just let it go. You can just tell, okay, Screw it, I'm not gonna fix this thing because maybe the problem is unsolvable. No, it can't be unsolvable because this is basically yeah, what could I tell? This is basically the problem which has like limited number of problems. This could be a limited number of components. This could be. So okay, now let's check debug connections here. So there might be some debugs which are strapped somewhere. At least on the previous CD217 version, there was I think there were like 4 straps. Each were really critical, because if you have them floating, the chip will go in some debug mode, or maybe it won't load its firmware on something like that. So let's check it. Let's also check that there's nothing wrong with power supply for our beloved Thunderbolt, because there were very rare cases where Thunderbolt power was actually shorted and the Thunderbolt controller somehow prevented CD3215 in it. It was on the older boards. Let's take a donor board. Yeah, alright. I've got this donor board, and probably I misunderstood, so the topper chip wasn't replaced, so this is the first thing we're gonna do now. Because basically the idea was to swap both of them from the GNOME good board, and this is exactly what I'm going to do. So maybe the problem is still there on the master chip, so it was replaced, but it was different one, not really proven good. And this one is 100% working, so we will replace it anyway. And let's get our stuff here. Actually, I thought that we are going to use logic analyzer here, but it's not really that deep. We just wanted to read firmware. Then we'll take a look. But it's weird that ESD was shorted. But if it was shorted, probably that would also indicate that there was something really dangerous happened to this board. Okay. So this one is bad. This one is good. Maybe. Okay. These magnets are always so hard to take apart. Oh, this one is really stuck together. Let's put something. So that's also one reason to buy iCloud locked boards, because iCloud locked boards will provide you a cheap 100% working set of chips, both PMICs, charging ICs and so on. It will be a little bit loud, this solder, but not for long. Okay. Well, it will work now. This will make this repair trivial as well. Let's hope we won't need more paste. Okay, now let's clean it, remove. Okay. Okay, now let's put this chip. Okay. Let's cool down the board. Let's clean it and let's test. This board needs more cleaning after that, but first we need to fix it. Also replace ESD diodes. We have the same, nothing changed. Yep. So now we know for sure there's something wrong around. Okay. That's same and that's same. That's weird one. Okay, let's check if it's soldered properly. Once again. And there's not much stuff here, you know. Okay, now we tapped it a little bit, so probably I have solder joints, like blobs. Well, hopefully not, but Okay, absolutely the same. Everything's fine here as well. This is not fun anymore. This is a hard one. For no good reason. For no good reason. Let's check in thermal. Maybe there's something, because there are like current spikes here and there. They are, yeah, so the capacitor charging and whatsoever. But so basically how this chip operates. So first it boots from its internal boot ROM code. This boot ROM code checks very simple things like if they're over voltage or if it's proper working conditions, and it allows current through, so it simply allows 5 volts to the system. And then it awaits to see 3 volt from the system, then it will read SOC ROM, Thunderbolt ROM, and after it reads Thunderbolt ROM, it reads its power delivery profiles. It is able to talk with SOC, and SOC tells it to communicate with the charger. So it does some like power negotiation, and then it gets what it needs. And yeah, so that's roughly how it operates. So there's not much stuff to be broken here. Since we have boot loop, we can look and maybe find if something blinks here with the temperature. Something is getting a little bit warm here. Not sure it's supposed to. Let's cool it a little bit down. Okay, so this would be this chip over there. So this is some small LDO. And it's totally fine, I believe. So just allow some power through. So 3.2, 3.8. So absolutely nothing wrong. Hard to see if everything gets hot on the Thunderbolt controller, but I don't think so. Okay, let's probably still swap SPI ROM. I don't think it will bring anything, but now we have like the whole set of SPI ROM plus CD3217s. Believe me, in the end it will be something really obvious and really trivial. Something I overlooked because I looked like somewhere else elsewhere. Like I didn't look for the more complicated stuff where it should be much simpler problem or whatever. It's almost always the case. Oops. Let's put it back later. Okay. Let's let it cool down. And let's put our chip back on donor. If we need it sometime. Where's the SPI? Here. Oh, it was a bad SOC-ROM. Interesting. That's very, very interesting. Now we have 20 volts and all this stuff and all this shit, but how exactly did the SOC-ROM died? Because it wasn't even connected to the chip which was broken. Let's find out, let's try to read it. And let's find what's exactly in its contents and so on. I think there's this one. Because the second thing of not fixing MacBooks I hate is fixing MacBook not understanding how exactly did it die and how exactly was it fixed. Because I have absolutely no logical explanation why this chip died, and also how exactly did it die in fashion that it doesn't allow anything, you know, like even try to the master out slave in communication, not even a clock signal, nothing. So let's see at least if it's readable. I think I have some amount of bismuth solder on my solder tip. Maybe I forgot to clean it properly. Okay. Come on. So now it's cool. Let's check. All right. Okay, so chip ID error. Let's check if it's wired properly because I didn't use this board yet. Okay, so it's fine. I check soldering once again. Nothing connected to ground. Everything's fine. Okay. Yeah, it's completely dead that you can't read it. Let's look in diode mode. What is going on here? Okay. So which one is ground? I always forget. So this one is ground. Hmm. Smart identifier. Let's check it. Yeah. This chip is completely dead. Wow, okay. So basically, as I promised, this absolutely trivial and obvious repair, yeah? So if you do everything right, and if you do, like, if you don't have any shorts, if everything works, if you have if you did test it from battery and so on, and you know that there should be the problem with the chip itself, go and check Thunderbolt SPI ROM activity, and if there is no activity, probably replace it simply. If there's some activity, maybe it's still worth to refresh it, so to zoom it up, so the power sequence looks approximately like that. So this chip, first it allows 5 volt to the system, so then we have ESL 9240, it makes PP bus 12.3 volts, then we have 3.8 volts and some other rails, and after at some point we also have 3.3 volts from the system, and it kind of acts as a trigger for it to read the SPI ROM, so Thunderbolt ROM, then it boots like the second stage and it's ready to communicate. It also feeds this firmware to the secondary chip, because the SPI ROM is one here, it's only connected with one chip, and this chip basically sends the firmware to another. So if the master chip is broken, or if something wrong with it, then the secondary chip won't get any firmware, so it will be also brain dead, or at least half brain dead. But the main thing is that CD3217 needs only power rails to read Thunderbolt ROM. If it doesn't read it, then look in the direction of the Thunderbolt ROM. Now, still, let's check here. So it was, if I recall, the bad chip was hot on this place, on this spot, and there's no explanation for that. Okay, but anyway, that SPI ROM chip is actually it's not really the first thing you expect, actually, especially if you have broken secondary chip, the slave one, which is not really connected to the ROM. I wonder how exactly did it happen. Okay, let's restore ESD diodes, so the protection is important. So this is not really educational video at the end of the day, just another raw video, raw repair. Not very useful, because basically what you have seen is that I spent an hour looking for the very obvious problem. But it's always something simple with charging circuit, because charging circuit is simple. All right. So that's it for today. I hope this thing will work fine, and once I have a more interesting case of CD3217, I will make a proper educational video, because this one is just simply a dump repair one. Cheers.